So today we're going to be covering part D of this homework, and we're going to start off by um, deriving a function of temperature whose root yields an adiabatic flame temperature. Now, when we talk about an adiabatic system, that means heat is neither lost nor gained in that system, so our heat remains constant. So when we talk about something like this, so let me say we have some reaction happening in a reactor. We have CH4 plus O2, which combusts, and we get CO2 and H2O. Now this just looks like your standard little chemical reaction equation. So we need two O2s, we need two H2O, make sure that each side of the equation balances. And if we say that on this side, our temperature equals room temperature, so 298 Kelvin, and we go to some final temperature which is going to be higher than the initial temperature, then we can use our theory of adiabatic systems to go and try and find this function of temperature, how much that we are going to increase this heat by with this adiabatic flame. So first things first, let's go over what I've drawn over here. This is kind of what our reactor is going to look like. We have an inlet here, some outlet here. And so at this inlet, we're going to be putting in CH4 and O2 at some initial temperature. And we will be putting out CO2 and H2O at some final temperature. So we can go ahead and use energy balances to try and create this function for this adiabatic flame temperature. The thing we can look at here is the enthalpy of the system. So if we were to take a look at the enthalpy, it'll look something like this, where we have the heat of CO2 at some temperature and be equal to the heat of formation of CO2 at 298 Kelvin minus the specific heat times the difference in temperature. This is the initial temperature here. But this is assuming that our specific heat remains constant. Now, it's not necessary that it has to remain constant, so we can definitely represent it in a way that takes into account that we have some variable specific heat. And that's differentiating the specific heat with respect to temperature over this temperature range here from 298 to the final temperature. So we can go ahead and differentiate it. I'll just do a little denotation, this little prime symbol here, and we can go on to start creating our energy balance and, you know, really getting into the nitty-gritty details. So now let's look at our energy balance. Now, our energy balance is going to look very similar to one of the previous videos that I did here, where we're going to have a description of the energy of the system. So we have our kinetic energy, our gravitational potential energy of the system, and it's going to be equal to the enthalpy N plus the kinetic energy N plus the gravitational potential energy N, all multiplied by a differential amount of mass coming in. And it's going to be the same thing out. And we also have some differential non-flow work and some differential amount of heat. Now, a couple assumptions can be made. The first assumption of which is that we are not really going to have this dq here, because adiabatic system, no difference in heat. We can also assume a steady state. Steady. Oh, come on. State. So this is going to be 0. And we're also assuming that our potential and kinetic energies are also approximately going to be 0. There's not a lot of change in that. So all in all, what we end up with is 0 equals h in times differential amount of mass in minus h out times differential amount of mass out. Now, we are assuming that no mass is lost within our reactor, so dm in equals dm out. That's a common term there. So eventually what we end up with is the enthalpy in is equal to the enthalpy out. So now we can pull up ChemCAD and proceed from there. So what we are looking at right now, this is the physical properties that is produced by ChemCAD, and we are very interested in this equation right here, equation 107. So it is this big long thing right here, and what we must do is we need to find the integrals of these internal components here, the c over t over the sine hyperbolic of c over t, same thing for this one with e over t, and we need to integrate that with respect to temperature. So what I'm going to do, I'm going to put this on a second monitor. I'm just going to write this down here. So let's see. We want to find the integral of c over t over sine hc over t dt, and then we also want to find the integral of e over t cosine hyperbolic of e over t dt, and then we're also going to want to find the integral of the entire thing. I'm just going to write that as that. So what we can do now is we can pull up Wolfram Alpha, pull up a new tab here, and just type this in really quick. I'm going to move my mic just so it's out of the way a little bit. But we're going to go ahead, we're going to go to Wolfram Alpha. And let me go ahead and just... So we want to integrate so first c over t over sine hyperbolic c over t just put a big old bracket over all that with respect to t Okay, I have it now. So it looks like our answer for this one, back please. Our answer to that is going to be c times, and it says the cotangent hyperbolic, however, NumPy doesn't do the cotangent hyperbolic, however, it can do the 1 over tangent hyperbolic, 1 over tangent hyperbolic of c over t. And so now we can do the same thing for this e over t with cosine hyperbolic and we get uh, I don't want it to detect that. I want it to detect E as a. We'll put a dummy variable in there for now and just see if it works that way better. Note that D is just going to be E in this case. Okay. So we get negative D tangent hyperbolic. Well, negative E actually. Tangent hyperbolic of E over T. Now, the last thing we want to do is we want to do the integral of the entire equation 107. So let's take a look at that again. So this is going to be, let's see, how do I want to do this? A plus B, A plus B times the C over T sine HC over T squared. Well, this is going to be sine. I don't want it to do that, however. Why is it making me do that? There we go. 2 and plus D times that. So I'm just going to copy this. Control C plus D and instead of E, let's use F because for some reason it doesn't want to play nice when we use E. So cosine hyperbolic, double check. Yep. Looks good. Okay, and let's run it. So what we get here, smooth this over a bit, is AT plus BC 1 over tangent hyperbolic C over T minus DF, or I guess DE, tangent hyperbolic of E over T. So now that we've got our integrals for everything that we need to do, we can move on. So now what we have here is the integrals of our equation 107. We have our equation for the heat of formation. Or I guess this is the equation for the enthalpy. And we also have our energy balance equation. Now, what we are going to end up doing is we'll assume 100% combustion, and we're going to calculate the adiabatic flame temperature for a natural gas that comprises of 95% methane, 4% ethane, 1% propane, and 200% excess air. So let me pull up this here. And what this is, it's a huge database that has all these text files with important data on different chemicals. And we also have this. Now this I'm very interested in because this will allow us to import all that data right there. So we'll wait for this to connect, and while we do that, we're going to import numpy as np, and from scipy optimize, we'll import root. Let's see. All right. Wonder where that is actually. Maybe that'll help fix it. Yep. All right. So now we are ready to start importing all of our data. So the way to start importing that stuff, the key behind this is the fact that we are importing the props class. And so what we can do is p is going to be equal to props. And we can import an array of things that we want. So let me pull up the whiteboard on my second monitor here and just see what we need. It seems that we need methane, so we're going to go methane. Maybe there we go. Import methane. We're going to import ethane. Going to import and propane. I wonder if it does this. I can go back and double check that later. And we have 200% air, so that's going to include our oxygen, our carbon dioxide, our water, our I believe that might be it. Let's see if I'm missing anything. It does not seem like I am. So there we go. Going to go ahead, import all of that data. And what we're going to do now is we're going to define our functions to go ahead and calculate a couple things here now. One more thing I missed. We also have nitrogen in air, of course. So nitrogen. And now we should be good to go. So we're going to define the integral of our CP, our specific heat, with that temperature. And we're going to return, let's see, what are we returning here? We are going to return, so in order to call the coefficients, the way to do that is CP ideal gas, and then the coefficient that you want, P dot actually, CP IGA times T plus P dot CP IGB I'm just going to have this copy pasted just to make things a little bit easier. IGC times, or actually we could just go over numpy dot tangent h p dot cp igc over t. That should do it for that term. And then minus cp igd times cp ige times np dot tan h of cp ige over t. And that should do it for the integral of our specific heat. Now for the second one, which is going to be our enthalpy, we're going to return the heat of formation. So heat of formation of the ideal gas, P dot, heat of formation of the ideal gas. And then let me pull up my whiteboard. Earlier I had made a mistake where this used to be a minus. That's supposed to be a plus, so I've corrected that. So plus the int CP of T minus the int CP of 298. And that should more or less do it for the two functions that we're going to be using for this code. So let me come back to my whiteboard here one more time, just because I want to show you guys where something is going to come from. So in the original problem, we're saying that we have methane, which is CH4. We're going to have ethane, which is C2H6. And we're going to have propane, which is C3H8. Now, why am I showing you guys this? Well, we could do something a little bit fancy with that information. If I create a matrix where we have one row that is the number of carbons in the mix and one row which is the number of hydrogens in the mix, we get something pretty cool. So for this first one, we have, for the methane, we have 1 carbon, we have 4 hydrogens, we have 2 carbons and 6 hydrogens, and we have 3 carbons and 8 hydrogens for each of these 3 components here. Now, if we go back and we look up the percentages for each of these, we have 0.95% for our, we have 0.95% methane, or sorry, 95% ethane, 4% ethane, and 1% propane. So what we get when we multiply this 2 by 3 matrix by this 3 by 1 matrix is we end up with a 2 by 1 matrix in which we are given the number of moles of carbon and the number of moles of hydrogen. And given this, we can go ahead and we can still create, or rather we have a better idea of how many moles of CO2, H2O. We have a better idea of how many moles of each of those things are in there. So given this theory here, with this 2 by 1 matrix, we can go ahead and we can proceed on with this problem. So let's get to work. We start off with the excess amount of air we have in this reaction. So that's going to be equal to 2. Let's start with our fuel comp matrix, which equals np dot array 0.95, then 0.04, 0.01. And then for our matrix M, we'll call that M because it's the amount of moles. We'll go create this array where I have 1, 2, 3 for the carbons, and then we have 4, 6, 8 for the hydrogens. So we're going to get the number of moles of carbon first and then the number of moles of hydrogen. So we're going to unpack this matrix multiplication. So it's going to be M, and then at is the matrix multiplication symbol, and then fuel comp. Right? And let's just check it out really quick. So NC, it looks like we get about that many moles, and H, get about that many moles. Okay. Cool. So now we can determine the number of moles of CO2, because that's just going to be the number of moles of CH, or the number of moles of carbon. All the carbon is going to go into the CO2. Number of moles of H2O is going to be the number of moles of H2 or crap, the number of moles of H divided by 2. We can also calculate the moles of O2. First, the stoichiometric amount. And that's just going to be equal to the moles of CO2 plus the moles of H2O divided by 2. And thus we can also calculate the total amount of O2 in the system by multiplying the stoichiometric amount of O2 U by 1 plus the excess air. Lastly, we want the moles of nitrogen, as that is still part of the equation. And so we can get the moles of nitrogen coming from the moles. So we know that the ratio between the percent nitrogen and percent oxygen in the air is 79 to 21. So if we multiply 21 by the moles of O2, we will get the moles of nitrogen in this system. What we want to do is write our expressions for moles in. And the way we're going to do this, I'm going to use np.concatenate. And we are going to concatenate the fuel comp array. So fuel comp. And we're going to concatenate this array that includes our moles of oxygen. We don't have any moles of carbon dioxide or water yet, so those are going to be zeros. And then our moles of nitrogen. Now for our moles out, we're just going to have one single array. There we go. We're going to have one single array, and we're just going to go in the same order that we see up here, making sure that this knows the order of what we have up there, right? So we first have our methane, so that's going to be our, let's see here. So we're not going to have any more methane. We're not going to have any more ethane. We're not going to have any more propane. And we're not going to have any more oxygen. Because remember, this reaction is going until completion. There's 100% combustion here. Now for our oxygen, we want to multiply the moles of our oxygen, the stoichiometric value, by the excess amount of our air in the system. For our carbon dioxide, that's just going to be our moles of CO2. For our water, that's going to be our moles of water. And for our nitrogen, that's just going to be the same thing there, because nitrogen is not being used in our reaction here. It's not part of the reaction that we look at. So let's go ahead, let's finish this off and round this out. Now the last thing to do is define one final function called hdiff, the difference in enthalpy, where we have an input of T. Now we want to return the dot product of the moles in times the moles in 298 minus the dot product of moles out and T. And if it all works, let's see what happened here. Give me a moment. Oh, I just forgot to redo this as an array. And then we want to have, I guess, maybe this here? Oh, not that. This here. Oh, and this needs to be the predefined function for enthalpy. And so does this. Now if I do it, no issues. And now what we can do is let's just run a test case. And we're going to use the root function. So we're going to try and find the roots for hdiff to converge at a temperature, say 1000. So let's try it. Oh boy. Okay, let's see if I got it to work here. And boom, we converge. Oh. Let me check. So one other thing that might need to be changed here. Let's see. Aha. So there is a bit of a conversion crisis here where we have a unit in kmols. And so the issue with that is that we have everything here in kmol. And so in order to fix this problem, we can go up to here to our integral of Cp, and we divide this by 1000, I believe. Yes. Now we get, yes, we get a temperature in the thousands range. So that is the adiabatic flame temperature for this reaction.